Hello and welcome to section 8.1. We'll be talking about angles of polygons in this section. A polygon is a closed figure formed by a finite number of coplanar segments called sides, such that each of the following conditions are met. The sides that have a common endpoint are non-collinear, and each side intersects exactly two other sides, but only at their endpoints, called the vertices. A diagonal of a polygon is a segment that connects any two non-consecutive vertices. So basically it comes down to a polygon being an enclosed figure. That's what that definition states. Here's some real life examples of polygons. Stop sign, we see that's an octagon. Here's several different washers and bolts that have different shapes. We see geometric shapes in nature and hexagons from a honeybee hive and a honeycomb. Question, how many degrees does a triangle contain? Well, we all know that to be 180. All the sides of a triangle add up to 180. And then the question is, how many triangles does a quadrilateral contain? Now let's look at that. Here's a quadrilateral, a four-sided polygon. And if we draw a diagonal, we'll see that it's broken up into two distinct triangles. So we can kind of think of it as the number of the degrees of a quadrilateral is the same as two triangles. That'd be 180 plus 180, which is 360. Let's talk about a hexagon and this idea of making triangles out of the hexagon. So we're going to pick one vertex and we're going to draw diagonals connecting the other vertices. So there's one, there's another, and there's another. So as you can see here, we had broke this hexagon into 1, 2, 3, 4 triangles. So in essence, we could take 4 times 180, and that would give us the sum of the measures of a hexagon. So here's a chart which kind of maps all of this out. Triangle, quadrilateral, pentagon, hexagon, heptagon, octagon. That's the number of sides they have. And if we were to connect the vertices from one vertex, these are the number of triangles that would be formed. Obviously a triangle has one, but if you go all the way down to an octagon, it could be broken up into 6 triangles. And then finding the sum of the angle measures is just that easy. It's that number of triangles you found times 180. And these are all the sums of the measures of their angles. Is there a formula that would go with this? Is there a nice simple formula that would work just to give us the sum of the interior angles of any polygon? Well, if you look here, it all depends on multiplying by 180, and then the number of triangles that are formed. Let's see if there's a relationship between these. Here's the number of sides 3, number of triangles 1, number of sides 4, number of triangles 2, 5 to 3, 6 to 4, 7 to 5, and 8 to 6. As you can see, we're subtracting 2 from the number of sides, then we're multiplying by 180, and that's going to give us our sum of the angle measures. Here's the interior angle sum theorem, and here's that very formula we're talking about. If a convex polygon has n sides and S is the sum of the measures of its interior angles, then S, the sum of the sides, is 180 times n minus 2. For this formula to work, all you need to put in for n is the number of sides. That's all there is to it. The exterior angle sum theorem. Now, their polygons also have interior angles. They also have exterior angles. And if a polygon is convex, then the sum of the measures of the exterior angles, one at each vertex, is 360. And here's a diagram kind of showing these exterior angles. So we got this pentagon, each of the exterior angles, there's all 5 of them. If we were to add them up, it would add up to 360. And that is true for all convex polygons.